Welcome, everyone. I am Dr. Kevin Woods presenting the article Climate Thermal Model Validation Against Empirical Data. My expertise is in thermodynamics and heat transfer, which is key in determining temperatures related to climate. I've published one book relating to climate modeling and have no financial disclosures. Renowned physicist Richard Feynman stated, "The first principle is that you must not fool yourself, and you are the easiest person to fool." In a previous article, I delved into a popular erroneous claim. The claim stated when atmospheric greenhouse gases are removed, the Earth's measured average surface temperature of 14 degrees Celsius decreases by 33 degrees Celsius to negative 19 degrees Celsius. Who makes this claim? Numerous well regarded government agencies, organizations, and even academic textbooks. So, why do they make this claim? It's from the blackbody radiator model. The model applies the first law of thermodynamics on a system, being the Earth, encompassed by a system boundary. An energy balance is applied with incoming solar energy, outgoing reflected solar, and outgoing heat emission. The end result is an average emission temperature of the Earth. Here is the energy balance in equation form. The solar absorbed is equated to the heat emitted by the Earth. Solving for the emission temperature yields the negative 19 degrees Celsius that was stated before. When compared to the measured surface temperature of 14 degrees C, the difference is 33 degrees Celsius. This is the logic followed in the claim. However, the logic violates the first law of thermodynamics. So how does it violate the first law of thermodynamics? Let's take a closer look. The system boundary only has radiation crossing it, and therefore is located at the top of the atmosphere. The system includes clouds, atmosphere, and the surface. The problem with the claim is that it states that the system is the surface only, without atmosphere or clouds. However, with the system boundary and the system as defined, you cannot make that claim. Here is a better look at it. The measured solar reflection by Earth is 30%, also known as Earth's albedo. In this picture, the highest reflection is due to clouds. The ground reflection is blue because Earth is mostly ocean with low reflectivity. Now, if you remove the clouds, you remove most of the reflection. Since the overall reflection, or albedo, includes clouds, atmosphere, and the surface, the emission temperature is a combination of clouds, atmosphere, and the surface. In fact, because surface heat emission is almost completely absorbed by the atmosphere, the emission temperature is closer to the average temperature of the clouds and atmosphere, not the surface. This is supported by the heat emission data shown. The surface is almost indistinguishable because most surface heat emission is absorbed by the clouds and atmosphere. It is evident that the heat measured in this data is sourced mostly from clouds and the atmosphere. Note how the clouds are much colder than the atmospheric emission. So if we reevaluate the model by removing atmosphere and clouds and applying the surface albedo and emissivity, the new equation is a gray body model yielding a surface temperature of 1 degree C. Note that the reflection is just the surface and the heat emission is just the surface. This temperature is more representative of a planet with no atmosphere, greenhouse gases, or clouds. The conclusion is the standard claims by government agencies like NOAA, organizations such as Encyclopedia Britannica, and academic textbooks are wrong. In a previous article, I developed a model called the stability solution model. The model provided annual average temperatures of clouds, atmosphere, and the Earth's surface. In this article, I expand the stability solution model to evaluate its validity in calculating annual average temperatures with latitude. The model contains 9 equations. The 9 equations are as shown. To understand how these equations are applied, we need to zoom in again on the Earth in the problem. For further detail, please read the previous article and this article, as there are many long equations. Two systems are defined. First is the surface, and second is the atmosphere and clouds. The energy balance on the surface is given as shown. The second equation is from an energy balance on the atmosphere and cloud system. Here, x sub c is the cloud fraction covering the Earth. The third and fourth equations are evaporation and convection. Water evaporates at the surface and condenses in the atmosphere, generating a pressure variation that causes a natural convection airflow. The equations are from natural convection theory as shown. First for evaporation and second for convection. Expanding shows the driving force of the natural convection given by delta rho over rho sub zero, which is the ratio of condensable gases to total gases, and calculated using water's vapor pressure at the surface and at the top of the clouds. The fifth and sixth equations come from a stability assumption in the previous paper and are the derivative of the first and second equations. These are applicable due to the clouds being able to rise and fall. The seventh equation is a correlation of a model for heat absorption varying carbon dioxide and surface temperature derived in this previous article. The correlation is given by the dashed line and approximates the model results given by the solid line. These model results are derived from first principles for atmospheric absorption. The eighth equation is a correlation from another article using a first principle derivation of atmospheric solar absorption and varies with latitude. The ninth equation is the variation of average annual solar radiation with latitude. This graph shows the average annual solar radiation given by the solid line, as well as the maximum daily average solar radiation in the dashed line. The equator has a relatively constant solar flux, while the polar solar flux varies significantly with time of year. Let's look at the results for surface temperature using the expanded stability solution model. The model surface temperature is shown by the solid line, and measured surface temperature is shown by the dashed line. The measured surface temperature is from the Climate Research Unit. The results show good agreement over 90% of the surface of the Earth. The major deviations are in the polar regions as expected from equation 9. The next part of the presentation is an evaluation of the effect of carbon dioxide concentration on surface temperature. The model was applied for two concentration, the pre-industrial concentration of 280 parts per million and the current concentration of 420 parts per million. The temperature distributions are shown with the highest variation in the polar regions. The increase in average surface temperature is 0.15 degrees Celsius, meaning since pre-industrial times, around 1880, humans most likely caused about 0.15 degrees C increase in average surface temperature. The graph shows the variation in average surface temperature varying carbon dioxide from 0 to 10,000 parts per million. The arrows show 0 parts per million, 280 parts per million, and 420 parts per million. The majority of the temperature increase due to carbon dioxide is experienced below about 100 parts per million, which is below any historic concentration of carbon dioxide. In summary, the expanded stability solution shows good agreement with measured data. Human-sourced carbon dioxide effect on surface temperature is about 0.15 degrees C since pre-industrial times, and the surface temperature varies non-linearly with carbon dioxide concentration. The largest effect is in the polar regions. Future work includes applying the model to evaluate other parameters, such as agriculture, which affects surface reflection, surface emissivity, land evaporation. Also, the model will be used to evaluate ice age processes. I'd like to acknowledge NASA Near Earth Observations website for the satellite data and images utilized in the presentation. For the entire article, go to the open access journal platform, prosjournals.com. Thank you very much.